Okay, so but anyways, I think it might be very interesting for people, because I have the feeling that video displays are also always nice. People think when we show this a lot in outreach projects, our 3D displays, and then of course people think that physicists are sitting in front of their computers and watching nice 3D animations. That's not the case. We are watching these MySQL tables or debugging code or looking at CI or whatever. But for students, it's extremely helpful to, when they join our collaboration, and then they just can open something and look at something, and they see the topology of events, etc. And it's also very helpful for debugging some events, because all these cuts we use to find interesting events or bad events or whatever, they might be nice on a terminal screen. But when you look at the actual event in a 3D display, it might reveal something like, oh, the nanobeacon was flashing, which we use for calibrations, and it looks like a shower in the reconstruction. And yeah, so for this stuff, it's very, very helpful. Okay, so this display is based on Makie for Cherenkov Neutrino Detectors. I wrote for now it's only for KM3NeT. You may know that at ICAP we have KM3NeT and P1 and IceCube people, so we can even work together. So let me quickly introduce KM3NeT, because we mentioned it a few times. So it's a Cherenkov-based neutrino telescope. We built it for at least 10 years now. It's located in the deepest seas of the Mediterranean. We have currently 2 sites operating. It's up to 3.5 kilometers deep in the sea. And when it's so it's like 2 detector blocks which are now built. There are more planned. But once it's finished, a full block is 1 cubic kilometer roughly. So it's a very big detector. And one detector block is displayed here. It's just some artist's impression. We have the normal configuration is 115 vertical strings, so up to 800 meter, each holding 18 optical modules. So this is one optical module. It's like this big ball, and each optical module has 31 photomultiplier tubes. So we have 64,000 PMTs in one detector block, which is quite nice. We see a lot of light, and we can do sub-nanosecond time resolution for photons. And the resolution for reconstructed muon events it goes down to 1 milliradian, which is very, very good and much better than IceCube. So we can much more easily map or find things in the sky, actually. Yeah, of course, there are other problems here, but just to show you how it looks like. So this is one string on the table, and this is how we deploy them. So these are kind of wrapped around a metal structure, and we drop it into the sea, wait until this thing reaches the bottom. Then some remotely operated submarine plugs in the power and the optical cables for the data transmission. And then this thing is released, and it unfolds, unfurls itself like a yo-yo or something like this. And then this structure can be reused for the next detector strings. Okay, so this is RainbowAlga.jl. The package I wanted to talk about is it's a pure Julia package based on this Makie. I'm using the GL backend, and it uses behind the scenes this GLFW to visualize, to show the window, and to interact, to allow interaction with the keyboard and the mouse. I use the same framework with PyOpenGL in my very old, like 10 years old Python implementation, but this is much better now. And of course, using Julia makes it much more possible to write more readable code. So I actually kind of neglected the old Python package because it was heavily optimized, and at some point you cannot read the code anymore. Okay, so it currently only works with KM3NeT data. It supports these funny root formats we have, and custom detector geometry and calibration data formats, but it's very simple, so it can easily be modified. And actually, a few people from P1 are already looking at it and want to visualize their own events, and also IceCube is interested. So it can be used for all kinds of similar detectors like Antares, Baikal GVDl, Trident from China. And the future aim is to give the user the full programmatic access to the actual scene. So you don't want something which you load and then design all kind of GUI elements to interact with it. But I imagine that it would be better to interact with it from the terminal. Like you can then programmatically steer the scene, create movies, and so on. Okay, so let's switch to the demo. I always hit escape, and this. So demo is, this is not the slide I wanted to show. Okay, so if you launch it, this is how it looks like. It displays the detector configuration which you load. So this is our current, one of the current detectors which are in the sea near Sicily. You can use the mouse to interact with it. You can see that this is the seafloor, and then we have these buoys which are holding, and then these strings which are containing these lines. You can zoom in, pan, and whatever. And here on the lower left side, you see a few parameters of the event. So it's currently at t minus 3,940. So if I press space, it starts to count, and you can use the arrow keys to accelerate it a little bit and go to t equals 0, where the actual event happens. And then you can see that here's some particle entering. So it's a muon entering the detector. And then all these PMTs are visualizing the signal. So the size of these blobs which are created is related to the PE, to the number of PEs detected. And they are also, so if the same PMT sees consecutive hits, then they are stacked on each other. So here you can see like these tiny things which are growing outside, so outwards of the DOM. I made it so that you can also visualize these hits, so they're not overlapping each other. So it's nice to see that the calibration is, so the compasses are working, because this one obviously has, so if you look at this, you can see that it's pointed towards the track, so it sees lights from the track, but of course we also have scattering. And yeah, so this is the spanning. You can see that it reached the end. And what we also can show, and what's quite unique for Cherenkov-based neutrino telescopes based in water and not in ice, is that we have an extremely good time resolution and almost no scattering or near the track. So if I hit C, I can cycle the color schemes. And this one is a color scheme which encodes the color information. So before, the color information was like early hits are reddish and late hits are greenish, or in other schemes, even other colors. But in this one, it's red when it's blue when it's basically on time with respect to the Cherenkov hypothesis. So you can imagine that a charged lepton is going through a detector, creates Cherenkov light. And if it's really dark blue, this means that it arrived exactly at the same time where you would expect a Cherenkov photon from the track hypothesis. So even it's a reconstructed track or a Monte Carlo track. And then it goes to red. Dark red means more than 50 nanoseconds off. So we are really within these 15 nanoseconds of time resolution along the track. And that's quite impressive. Yeah, and we also have dark mode. Implemented dark mode for people who prefer this. And all the different. So this is the color scheme which works for dark mode very nicely. Yeah, so that's all basically. If you have any questions, you can look at the source code. As I said, it's not really, it's still work in progress. So there's a lot of things to do, but it basically shows you how to do event handling, like how to recognize key presses from the keyboard, or how to set up camera which rotates, and all the stuff. So it might be helpful if you want to do something similar here in your experiment. Yeah, you can find the source code I hope I put the source code somewhere. Where is the link? Yeah, there. Page number 4. Okay. Yeah, that's it.